For the second speaker, it's a distinct pleasure to introduce Dr. Jeffrey Tsao from Sandia National Laboratories. His presentation is also in the general field of solid-state lighting. He is a visionary of this field, and approximately in the year 2000, he co-authored a very important article that laid out the vision for solid-state lighting, that laid out the vision of replacing conventional light sources by solid-state light sources, and he and his co-authors pointed out the wide range of benefits that at that time were not known to the technical community and to the society at large. So that was a very important paper that influenced the course of solid-state lighting in a very profound manner. Now, Jeff Tsao is a principal member of the technical staff at Sandia National Laboratories, where he studies the integrated science, technology, and economics of energy technologies. He received his PhD in 1981 from Harvard University in applied physics, and he has co-authored more than 150 publications. He is also the author of a monograph of a book on materials fundamentals of molecular beam epitaxy. And he's a fellow of the American Physical Society and the AAAS. Please let's welcome Dr. Jeff Tsao.
Hello. Testing. Thank you, Fred, for the Thank you, Fred, for the very kind introduction, and thank you for the invitation to speak here today. It's really an honor to be here. It's a special honor to be speaking after Shuji Nakamura. Professor Nakamura, of course, has made so many tremendous contributions to solid-state lighting as well as many other fields. So again, it's just an honor. Not too long ago, as Fred mentioned, the idea that solid-state lamps would compete with traditional lamps in anything more than just niche applications was really just a dream. Now, however, we really stand at the threshold of a massive transition in which every lamp on Earth, I believe, will be a solid-state lamp, all the way from your smallest signal lamp to your largest stadium scale flood lamp. So what I'd like to do today is give an overview of solid-state lighting, but I'd like to start by putting solid-state lighting in a more general perspective of lighting as a whole, and throughout I'll try to blend various perspectives ranging from science, technology, and economics. So here I show a composite satellite photo of night coming to Europe and Africa. And I show this photo to illustrate the importance to human society of light, and particularly artificial light. As the sun sets, the artificial lights go on. In fact, this photo even underrepresents the importance of artificial light to human society. We probably consume just as much light, at least as much light, during the day as we consume during the night, because so many of us spend so many of our working or waking hours indoors, protected from the environment, where we would still like to be productive, and so we still want to consume light. So because lighting, and particularly artificial lighting, is so important to us, we have expended a lot of ingenuity as a human society on improving the technology for lighting. So here on the left, I show a 300-year history of artificial lighting, the efficiency of artificial lighting. The left axis is luminous efficacy, eta, in units of lumens per watt, lumens of visible light that you can create per watt of input power, either electrical or chemical fuel power. The bottom axis is the cost of energy in units of dollars per megawatt hour. And here I show a number of data points for various nations and groups of nations over the past 200 or 300 years, UK in 1700, the world not on grid electricity, the undeveloped world not on grid electricity in 1999, and a number of data points corresponding to the modern world in the 2000s. As many of you know, the cost of light is dominated by the operating cost of light, and the operating cost of light is simply the cost of energy divided by the luminous efficacy. Okay, so to show the progress that has been made in the cost of light, here I show contours, these dashed diagonal gray lines, contours of constant cost of light, all the way from $100,000 per megalumen hour down to $1 per megalumen hour. And you can see that over the span of 200 or 300 years, the cost of light has decreased by an astonishing 4.3 orders of magnitude. Now, of that 4.3 orders of magnitude, 1.5 orders of magnitude is due to a decrease in the cost of energy during that time. But the much larger fraction, 2.8 orders of magnitude, is due to the increase in luminous efficacy over those years. Now, this is just telling us what we already sort of intuitively know, which is that lighting technology has made enormous progress over the past 300 years, all the way from candles at less than 1/10 of a lumen per watt, all the way to gas, kerosene, and modern electric lighting, nearly 100 lumens per watt. Okay, as one consequence of this decrease, astonishing decrease in the cost of light, we have benefited by being able to consume more and more light. Lighting is good for us. We like light. It makes us more productive. And so here on the right, I show a similar 300-year history of the per capita consumption of light. This left axis is per capita consumption of light, phi in units of megalumen hours per person year. This bottom axis is sort of a funny quantity. It's a fixed constant beta times per capita GDP, per capita gross domestic product, divided by cost of light. Now, because per capita GDP has the units dollars per person year, cost of light has the units dollars per megalumen hour, this quantity has the units megalumen hours per person year, which is the same as the units on the left axis. And what you see is that if you choose beta to be this constant 0.0072, these data points pretty much fall on a line of slope 1. Okay, so that has two implications. One implication is that over the past 200 or 300 years, human society has expended about 0.72% of its GDP on light. That was true in the UK in 1700, true in the undeveloped world, not on grid electricity in 1999, and true for the advanced world in the 2000s. On a 2005 world GDP of about $60 trillion, 0.72% corresponds to about 440 billion US dollars, so this is a fairly large amount. And because of the energy intensity of lighting relative to other goods and services, this actually corresponds to a much larger percentage, 6.5% of the world primary energy consumption. So on a 2005 world primary energy consumption of about 16 terawatts, this corresponds to about 1 terawatt. So the point I want to make with this view graph is that lighting is important to us. We want to consume more and more light. And because we want to consume more and more light, it is of continuing importance to increase the luminous efficacy or the efficiency with which we create that light. So that brings us to solid-state lighting, which is poised to increase the efficiency of lighting by yet another 1/2 to maybe 3/4 of an order of magnitude. Now, to put that in perspective, that will not be the largest increase in efficiency that has happened over the last 200 or 300 years. That honor probably resides with incandescent lamps, which improved the efficiency by a little bit more than an order of magnitude. Nevertheless, 1/2 to 3/4 of an order of magnitude is nothing to sneeze at. It's something that's very important. And in fact, solid-state lighting has the potential, as Professor Nakamura mentioned, of perhaps approaching even 100% efficiency. Okay, so now let's turn to solid-state lighting. And first, let me start by asking, what do we mean by this 100% efficiency? That is to say, what is the most efficient lighting source that you could create, given what we know about the human visual system, and also what we know about the colors of objects in the environment and the world around us? Now, this question has been asked several times in the past decade. Here I show some relatively recent results based on a simulator by Yoshi Ono at NIST. Basically, what the simulator does is it takes 4 RYGB wavelengths, varies their wavelengths and relative powers to maximize luminous efficacy for a given color temperature, and also a given ability of that light source to faithfully render colors in the environment around, of objects in the environment around us, something known as as many of you know, the color rendering index. Now, why 4 colors? Why RYGB? The reason is that most objects in the world around us have relatively broad reflectance spectra. And because they have relatively broad reflectance spectra, it doesn't take very many colors to distinguish between them. Turns out 5 is overkill. 3, you can do a pretty good job of representing almost all, distinguishing between most objects, but 4 is safe. And so in this simulation, we've chosen 4 to be conservative. And here I show the results. If this is something that many of you probably already know, there is an inverse relationship between luminous efficacy and color rendering index. If you increase luminous efficacy, you decrease color rendering index. If you decrease luminous efficacy, you increase color rendering index. And the reason is that these two things are fighting each other. If you want to maximize your luminous efficacy, of course, you want to put all of your light, concentrate all of your light right at the peak of the human eye response at 555 nanometers. But if you want to render colors of the world, of objects in the world around you, you want to diffuse your spectrum away from 555 nanometers. And to illustrate that, here I show at the bottom the reflectance spectra of the so-called Munsell samples, the 8 Munsell samples that are used to calculate the color rendering index. And you can see that they span a range from, say, 150 to 200 nanometers wide. And so as you increase color rendering index, you basically move the optimal wavelength, position of the optimal wavelengths away from 555 nanometers. And as you do that, you decrease your luminous efficacy. Now, as many of you know, a CRI of 70 is okay for flashlights, but not good enough for general illumination applications for reading, for example. A CRI of 80 is good for many applications, and a CRI of 85 is considered good for almost all but the most demanding general illumination applications. So here we've chosen 85 to be conservative, and at a CRI of 85, you see that you can achieve a 400 lumens per watt luminous efficacy. So this is sort of what one can consider, at least at a color temperature of 3800, what one might consider 100% efficient lighting. And the wavelengths, as you see here, correspond to 459s, 535, 573, and 614 nanometers with these relative powers. Okay, so how does this compare to the current generation of traditional lamps or available lighting technologies? Okay, so here I show the spectral power distributions of a number of light sources. The white curve is the spectral power distribution of that 100% efficient light source that I just mentioned. So you see there's 4 peaks, and by and large, most of the spectral power is within the human eye response, although you can see that the red line at 614 nanometers is a little bit in the fringe, in the wings. The blue line at 459 nanometers is definitely way in the fringe of the human eye response. Okay, in red, I show an incandescent lamp. As many of you know, incandescent lamps are very efficient at converting electrical power into optical power. The problem is that most of that optical power is in the infrared, where the human eye isn't very sensitive, and so you end up with something that's only 3.5% efficient. Here in the blue, I show a fluorescent lamp. As many of you know, fluorescent lamps are basically mercury discharges. You lose about half of your efficiency in the discharge itself exciting the mercury line, and then you lose another half of your efficiency down converting your mercury line into the visible. So you end up with something like 20 to 25% efficiency. Okay, then here I show a commercial 14% efficient, 58 lumens per watt solid state lamp. Now, some of you may be accustomed to seeing bigger numbers than this. We heard much bigger numbers from Professor Nakamura's talk. And the reason why these numbers are what they are is that I've chosen conservatively. This is a commercial device, not a research lab device. This is something that you could buy in late 2009, not something that may be coming out in early 2010. And at the rate of progress in solid state lighting, a few months actually does make a difference. This is also a warm white color temperature, 3100 K, and as many of you know, the cool white solid state lamps tend to be more efficient than the warm white, but they don't render colors as well. And so again, to be conservative, I've chosen a warm white. I've also chosen to drive this device relatively hard at 0.7 amps. And as many of you know, there is a phenomena that Professor Nakamura mentioned and that I'll mention a little bit more later called efficiency droop. And so at lower currents, you can get higher efficiencies. So again, this is a conservative device, so it's 14% efficient. So I'll talk a little bit more about this in a minute. I just want to point out a couple of things. One is that it is, of course, already more efficient than an incandescent lamp. And so it is better for you already to replace your incandescent bulbs with a solid-state lamp. But of course, it is not as efficient as a fluorescent lamp, and so it is even better for you to replace your incandescent bulbs with a fluorescent lamp, which is, of course, what is going on right now. The second thing I would like to point out very quickly is that although it is not the dominant reason, it is a contributing reason for why this efficiency is not as high as we would like, and that is that the spectrum, this black spectrum here, is not ideal. You can see there's a blue LED line here, then there's a relatively fat green phosphor line centered at 540 nanometers, and there's another fat red phosphor line centered at around 614 nanometers. The blue LED is too far to the blue. It is even farther than this perfect blue for the 100% efficient SSL, which is itself already in the fringes of the human eye response. So this is way too far out. The red is also too far into the red. There's too much in the deep red, further out than where this 100% efficient sort of red line wants to be. This is really in the shallow orange red, and therefore in the fringes of the human eye response, where the human eye is not very sensitive. Okay, so what are the factors that contribute to why this solid-state lamp is not as efficient as one would like? So here I show the anatomy of a state-of-the-art commercial solid-state lamp. This particular one is a thin-film flip-chip design pioneered by Philips Lumileds. It's basically a blue LED, 1 millimeter on a side, driven by 0.7 amps, onto which there are red and green phosphors. Some of the blue leaks through, some of the blue is absorbed by the red and green phosphors and re-emitted as red and green light. But when you look at the various sub-efficiencies associated with this lamp, actually they're not too bad. Consider, for example, this blue LED. Here I've itemized some of the various sub-efficiencies. The joule efficiency, what's remaining after resistive losses. Resistive losses are about 15%, so what remains is about 85%. That's not too bad. Internal quantum efficiencies at low power are about 70%. This droop that I mentioned at higher power is about 30%, so that leaves behind 70%. Again, that's not too bad. Light extraction is about 80%. So all of these numbers are really not too bad. It's just that if you multiply them all together, because they are all in series, you end up with something that's 33%. So it's sort of like death by 1,000 cuts. Each cut isn't so bad, but there's 4 of them, and so you end up with something like 33%. So the same for the phosphor in the package. The internal quantum efficiency of the phosphors themselves that are absorbing and then re-emitting is about 90%. They're actually quite high. The Stokes deficit, that is, you're converting a high-energy photon blue into green or red, So you lose some energy, some efficiency that way, about 20 to 30%. That leaves behind 76%, which is, again, not too bad. Scattering and absorption, after all, these are polycrystalline grains. They do scatter light, and that light can be reabsorbed somewhere. Still, that leaves behind about 80%. These numbers are not too bad, but again, you multiply them out together, and you end up with something like 54%. And then finally, there's this spectral response that I had mentioned earlier. The spectrum of the solid-state lamp is not ideal. It's too far into the blue and also too far into the red, so you end up with 78% efficiency there. Again, though, 78%, 54%, 33% isn't too bad, but you have to multiply them out together again, and death by 1,000 cuts, you end up with something that's about 14%. So the billion-dollar question, in a way, is how do we increase this 14% to something as close to 100% as we could possibly get. And in a way, that's a $440 billion question. That's how much we spend on light. Or you can consider it a 1 terawatt question. That's how much primary energy lighting represents. So let me just mention now some of the, in a sort of a broad brush way, some of the technology grand challenges that might enable some of these increases from 14% up to as close to 100% as one could get. Now, in choosing these three, that's not meant to say that there aren't a number of smaller challenges which, if you integrate them together, wouldn't equal or perhaps exceed any of these grand challenges. But I've picked these out as sort of representative of the major sort of single challenges that would enable much higher luminous efficacies. So the first one is to eliminate this blue LED droop that, again, Professor Nakamura mentioned and that I mentioned earlier. And this blue LED droop basically has to do with somehow there is a higher order process, some non-radiative pathway that has some higher order carrier density dependence that kicks on at high current densities. And so you end up with this turnover in internal quantum efficiency. Now, I'll mention this a little bit later, but it turns out 200 amps per square centimeter is a drive current at which, if one could drive the current generation of solid-state lamps, would enable a cost structure for solid-state lighting to become very similar to that of traditional lighting. And so 200 amps per square centimeter is actually a reasonable target. And so the idea would be to somehow forestall these non-radiative processes, whatever they are, so that they don't kick in until you get past 200 amps per square centimeter. So that's sort of a reasonable target. Okay, the second grand challenge might be called finding a narrow line width, shallow red color converter. Could be a phosphor, could be a quantum dot system, could be some kind of color conversion system. And the reason, as I had mentioned earlier, is the spectrum. Here I reproduced the spectrum of the conventional solid-state lamp, current generation solid-state lamp, and I've taken out the red phosphor as this red dashed line, and again you can see that it spills over too far beyond 614 nanometers, and where the human eye isn't very sensitive. So the idea is to find some sort of narrow line width phosphor that doesn't have that same kind of spillover, but is also in the shallow red around 614 nanometers. And then the third grand challenge is to fill in this red, yellow, green gap. As Professor Nakamura mentioned, the reason why we use phosphors is because actually the only really good visible LED we have is the blue one. Indium gallium nitride does very well in the blue, but peters out pretty quickly when you get into the green, yellow, and especially if you're in the shallow red. Indium gallium with some aluminum phosphide is very good in the deep red, but also peters out pretty quickly when you get into the shallow red, and certainly when you get into the yellow and the green. So one of the grand challenges here is to somehow find new semiconductor materials or re-engineer existing semiconductor materials so that you can fill in this gap. Okay, now so far I've talked almost exclusively about luminous efficacy, as if that's the only thing. What about cost? In fact, many people will say, well, it's really cost that's causing solid-state lighting to be not as competitive with conventional lamps as it could be. Well, I guess the answer to that is sort of yes and no. And to illustrate that, Here on the left plot, I draw the two main costs associated with lighting, not just solid-state lighting, but lighting in general. On the left axis is the capital cost of light. That's basically the cost of the lamp, amortized by its life, the lamp that's going to produce the light. And then on the bottom axis is the operating cost of light, which is basically the cost of energy that you're putting into the lamp divided by the luminous efficacy. Both of these have the units dollars per megalumen hour. And on this plot, you see I plot some red circles, which correspond to the main classes of incandescent lamps. The blue open circles correspond to the main classes of fluorescent lamps, and the green open circles represent the main classes of high-intensity discharge lamps. So those are all traditional lamps. And what you see is that they mostly, especially the bigger circles, which represent the larger market size lamps, the traditional lamps, by and large, fall on a line of slope 1, offset downwards from a 1-to-1 line by a factor of 6. Okay, so all this is saying is that the cost structure of traditional lamps is such that the capital cost of lighting is about 1/6 of the operating cost of light. So that just means that the dominant cost of your lamp of lighting is really the electricity that you're using rather than purchasing the lamp. Now, if solid-state lighting could have exactly the same cost structure, then in a sense we would be done. There would be not very much incentive to decrease the capital cost of the lamp by much further, because the main cost is already the other cost, the operating cost. Okay, so to see where solid-state lighting is now and where it has been in the past, here I show the last 5-year history of solid-state lighting from 2004 through late 2009. And you can see that actually the dominant improvement in solid-state lighting technology from an economic perspective has been a decrease in the capital cost of light. In fact, here I've sort of sub-analyzed this 2008, mid-2008 lamp. You can see that actually, so it's driven at, say, 0.7 amps. If you had driven it at a lower current, 0.35 amps, because of this efficiency droop that I had mentioned earlier, at a lower current, its efficiency actually increases, and so the cost of light, the operating cost of light actually decreases, but at the expense of a higher capital cost of light, because you're driving the lamp not as hard, you're not getting as much light out, so per lumen of light, the capital cost is higher. At the same time, if you could have driven it harder at 1.5 amps, then again, because of this efficiency droop that I had mentioned, the luminous efficacy decreases, so your your operating cost of light increases. Okay, at the same time, your capital cost of light decreases because you're putting out more lumens, and so amortized over the number of lumens, your capital cost is decreasing. In fact, if you could have driven this lamp at around 2 amps, 2 amps in a square millimeter package, so 200 amps per square centimeter, as I had mentioned earlier, you would have been roughly right on this 1-to-6 cost structure line, which means that basically you would have been done. The remaining improvements in solid-state lighting technology would be in luminous efficacy and not in cost. Okay, another way of seeing that is that the capital cost of light can be written as something that one could call the cost of a lamp that can sink a certain amount of power. I call that dollars per watt in, okay, divided by the luminous efficacy and then amortized by tau, the lifetime of the lamp. The operating cost of light, as I had mentioned earlier, is the cost of energy, also divided by the luminous efficacy. So both of these quantities have luminous efficacies in them. So if you increase your luminous efficacy, you decrease both your capital cost of light and your operating cost of light the same, linearly. And so if you are once on this 1-to-6 cost ratio line by, say, being able to drive at 2 amps or through some other manufacturing cost reduction, you will forever be on this 1-to-6 cost structure line through increases in luminous efficacy. And so the idea would be then to continue to increase luminous efficacy until you finally cross this fluorescence and HID magic final ownership cost. Okay, so what does this mean for the ownership cost of light, which is the sum of the capital and the operating cost of light. So here on the right, I plot that ownership cost for the same 5 data points as a function of year. And what you see is that 2008, or somewhere in the middle of 2008, was sort of the magic point at which the ownership cost of solid-state lights just went below incandescent lamps. And 2012, roughly, is where, if future progress is similar to past progress in solid-state lamps, and at least for the next few years, I don't see any reason why it won't be, 2012 will be the year in which solid-state lights cross just below fluorescence and HID. So, in a way, this brings us full circle. So I had started out at the beginning of my talk saying that we were at the threshold of a massive transition from traditional lamps to solid-state lamps. Now we know approximately when that might begin, 2012 or so. Of course, that's not to say that it will be fast. There's a huge infrastructure of traditional lamps out there and a huge infrastructure of sockets for those traditional lamps out there. So it will certainly take a lot of time, but 2012 may be the beginning of that transition. Now, one thing I just want to point out in closing is that, of course, it doesn't take that much to beat traditional lights. As I mentioned, they're about 20 to 25% efficient. So solid-state lamps just have to be 25 to 30% efficient, and they will gradually beat traditional lamps. So in a way, there's yet another challenge for the solid-state lighting community, and that is to not be too distracted, for the R&D community, to not be too distracted by the tons of money that will be made over the next 10, 15 years by commercial solid-state lighting companies as they displace traditional lights, and to continue to try to improve luminous efficacy, not just to 25, 30, 40%, but to get as close to 100% as possible. And with that, thank you for your attention.
Thank you very much for the presentation, and the presentation is open for questions. We have microphones in the aisle. Please, if you could please use the microphone in the aisle.
Yes. The economics is a little more complicated, as I'm sure you appreciate. In particular, rather than comparing the cost to the user, one probably wants to look at the cost to the electricity generator. The reason for this is that, for example, you see right now in many places that the electric power industry is supporting by discounts, et cetera, the use of compact fluorescent because they want to save on the construction cost of new generating capacity. So I assume you've looked at that. I'd be interested to know whether you come up with any different policy considerations based on that kind of analysis.
Yeah, that's a very, very good point. In fact, that's one of the reasons why, as Fred had mentioned back in 2000 when Roland Heitz, then at HP, and I wrote that white paper, one of the things that we were concerned about is that in some sense the benefits to solid-state lamps is in energy savings. Most of that energy savings is really sort of a general benefit to mankind as a whole. Maybe utilities are sort of a representative of that in some sort of sense. The benefit is not so much to the solid-state lamp industry. The solid-state lamp industry is really only, in a sense, 1/6 of the overall economic cost structure of lighting. And so to expect the solid-state lighting industry to itself invest the tons of R&D money that would be required to achieve near 100% efficiencies or to achieve improvements in efficiency is not realistic, because they are not the part of society that's going to benefit the most. So, but yes, that's a very, very good point.
You mentioned that there are 3 areas of material science for improving the efficiency, and the third of them, if I remember correctly, was finding materials that would fill the gap between the red, yellow, and the green. Can you say some more words about what would be the target band gaps or target dopability of those materials needed to fill those specific gaps?
Well, I can say that the 614 nanometer line is, I think, by far the most important one. The reason it's by far the most important one is that the green phosphor, after all, there's not very much of a Stokes shift in getting from blue to green. And the green is right smack in the middle of the human eye response, and so there's much more tolerance. You can have a broad line, it can be a narrow line, it really doesn't matter too much. The red line is where it's much more important because you're already at the fringes of the human eye response, and so you don't want very much spillover into the deep red. So that has to be a relatively narrow line that puts constraints on what materials or what engineered structures you use, and 614 nanometers is just a very tough wavelength to get to. So I would say that is by far the most important one. Not to say that it wouldn't also be very useful to have the yellow at 573 or the green at 535 with also semiconductor or electroluminescent materials, but I'd say it's the 614 that's
so which
more
direction have people already looked in to find a 614 material?
Well, 614, of course, using indium gallium phosphide is a possible option. People have looked very hard at trying to move that into the wider bandgap region, but that's been a very, very tough thing, especially when you want to drive them hard so that you can get the capital cost of the lamp down per lumen. If you drive them hard, that's when you start to get carrier spillover, all sorts of transport effects. There's the direct-indirect band crossover. There's all sorts of things in the indium gallium phosphide system, as you know, Alex, probably better than anybody else does, that are very, very tough. Perhaps indium gallium nitride will do it with nonpolar and semipolar substrates. That's also a very, a possibility.
Hello, I was just wondering about your perception of the relative difficulty of these three challenges.
I'm sorry, I didn't.
I was just wondering your perception of the relative difficulty of these challenges.
Oh, the relative difficulty. Oh, I would say number 3 is probably the most difficult. Seems to be the most difficult. Number one is something that's being attacked by tons of research groups all over the world, and I think it's a very exciting area right now. I am sort of thinking that over the next 5 years, there will be a lot of interesting conclusions in that area, and there will be new ways of circumventing the droop. And then 2 might be sort of in between. Yeah, 2 is also a very difficult challenge.